Welcome everyone. I'm going to teach you today about support vector machine, what they are, when it's suitable for us to use them, and how to apply kernel tricks, and a little bit of math about support vector machines, how they are working, how they are optimized to work. Let's go. Support vector machines is a supervised learning algorithm where you can use them for classification and for regression. You can use them to classify like dogs and cat, male and female, whatever like things into classes. Or you can use them for regression. You can predict them using them as prices of houses next year based on the data current year. You can predict future data based on the current data, or you can use them as a classifier where you can classify your data into different classes. As you can see in the figure, like if you have a data, the red data and the blue data, the supported vector machine is just a line which is separating the two classes of the data into class 1 and class 2, as you can see, with the widest margin, widest street. We need like the separator line have the widest street between the two data, so it's called support vector machine. That line which have dot lines is called the support vector, and we can calculate the support vector using those two kind of data. Those extreme data, we're trying to maximize that street to make it maximum, and those data, that point and that point is the support vector, which is like make it like it bounded by those kind of data. If I move that data, if I move that point of data or that point of data, the support vector will be wider like that. So those point of data is those extreme points where the data are so closed are the support vectors which govern the street width. Like if I moved a data from here or something, not going to affect the support vector machine. So those extreme points are the most important points in that algorithm, where those points are so close to each other. I'm trying to like draw a line with the widest street between the two classes of data. That's the idea behind the support vector machine. Let's see how we are going to use them and how to calculate that line. If I have I have here a comparison between logistic regression and linear regression. Support vector machine. I have here the logistic regression classifies those data into and separated them with a line, as you can see, and the support vector machine separates them with another line, with another boundary, with another slope, as you can see, like totally different separation. Like, which one is better? Which one of those things of the two classes is better? Is the logistic regression is better than the support vector machine, or the support vector machine is better than the normal logistic regression? Let's see. If I have a new data, the classifier which will work better with the new data is going to be the better one, the best one. So let's see if I have a new data which is closer to the class 1 data, which is closer to those data. Let's have a new data which happen to be close to those data. How the two classifiers going to work? Is that one going to work better with the other one? Let's see. I have a new data here, as you can see, that data. As you can see, the logistic regression classified with the red data and the support victim machine classify it into the blue data. Which one is right? Is that one or the second one? Let's see. As you can see, the distance from here to here is less than the distance. You can see that. So, and here is the distance, as you can see. So that classify them much more better than logistic regression. Support victim machine work much more better than normal logistic regression as a classifier. Let's have another situation where our data is like extremely close to each other. As you can see, our data is totally close to each other. Some data points are like overlapping. The red data are overlapped to the blue data. How we can separate them with support victim machine? What's the line we are going to draw to separate those kind of data where the data is like a little bit overlapped? If the data is a little bit overlapped, as you can see, we can draw a line with like a narrow margin. The problem with that is, like, if you have a narrow margin, a narrow boundary around your line, that classifier is going to work well with your training data. But once you are going to real life data, once you have a data from outside your training example, your classifier will suffer, will perform like very badly with the new data. That's problem called overfitting, where your classifier work very well with 100% with your data and perform very badly with new data. So we need to maximize that margin. We don't need our classifier to work like 100% with our data. We can make it work like 90%, 95%, and 5% wrong, and we have it to work with the same performance or better and with the new data. So we are going to accept that our algorithm going to classify some of our training data wrongly, so it can work well with the new data and we can avoid the overfitting. How we can make that? We are going to make it wider. We are going to accept some of data point like classified wrongly with the blue one, and accepting that going to make the plane the margin around the separation line, the boundary around the separation line to be maximized, and that's going to work well with the new data. And that line and the boundary around it is called hyperplane. In 2D, it look like a line, but in 3D it's going to be a hyperplane. Let's see. Like, you can apply the support vector machine in any dimension. Not only you are not only bounded to 2D. You can apply it to 2D, 3D, n dimension. Let's have an example where you have some data where you can't separate them, like those data. If we have some data like those data, how we can separate them? Let me draw a line here or something. Like that one is not going to be performed well, like it will classify 50% of the data wrongly. Or we can, like, as you can see, it's not double. You can separate them with a straight line. Luckily, there's a trick where we can transform those data into a separable data. We are going to transform those data from 2 dimension into a 3 dimension. So we can separate them with a hyperplane. Like that plane, we're going to separate them nicely. As you can see in the following figure, we took those data and transformed them into a 3-dimension, and we have a plan which is separating the two data, the two classes, into easily. That thing is called kernel. Like, we are not going to transform, like, especially if you have a huge data, transforming them into another higher dimension order is going to be computationally expensive. So there's a trick to solve that problem. Instead of transforming all the data into the higher dimension, then doing the calculation, we are going to do the calculation in the lower dimension, then we transform the result into the higher dimension, so it will be computationally efficient, and it will be much faster than transforming the whole data into another high dimension, then doing the calculation. So the kernel trick is like applying a kernel where we apply them on the lower dimension, then we transform the result into the higher dimension, so it will be faster. Let me give you an example which give you an equation about the kernel and how we can apply them. Okay, and let's go with the example. Let's have a data where we have if we have a line of data like that. Okay, and if we have points on that, like blue points, okay, on the data, on the line, okay, and we have the red points like that. Can we separate those data using support vector machine? For sure, it's easy. We can separate them just easy like that. And we have our hyperplane around them like that. Okay, that is so easy. Okay, imagine if we have the same situation with the data on a line, which is not a 2-dimension or something, just like a line, and like the data is going to be like the data I'm going to draw right now. Yeah. If you have your line, let me change the color. If I have that, if I have that line, okay, and my red points is like that. Okay, and the other class is like that. As you can see, to separate those points, like you can't separate them with a line. You can't easily separate them because they are overlapping on that line. How could we separate them? We apply a trick called binomial trick, where we transform those data into another shape. Instead of line, we just apply a square to every point here. We're going to square every point. We are going to square them every point. If you square them, okay, and I will show you how that is going to work. If you square them, that line going to be transformed into a parabola like that. Okay, and you are going to have your red point here, red points here, and you are going to have the blue points here. Okay, okay, so you can easily separate them with the support vector machine using applying the binomial trick. Either you can transform them into another dimension, higher dimension, or apply a binomial trick, or there's a lot of kernels. You can use Gaussian kernel or binomial trick, or even if you are working with neural network, you can use sigmoid kernel or 10H or any other kernel, famous kernels. That's only transforming the data from like a dimension to a higher dimension, so they can easily separate it. You can separate them easily. And I'm going to give you a little bit of math behind the support vector machines and how they are working. Okay. And we'll come back to the regression. Okay. The equation for a straight line is y equal mx plus c. Okay. That is the straight line. Y equal mx plus c. And by tweaking M and tweaking C, we can easily move the line between our data. Let me show you, like tweaking that one, increasing them or decreasing them, is going to rotate the line. Our line, that's the equation of the line, straight line, okay? As you can see, like tweaking the M is the slope of the line, okay? It's going to rotate the line around our data. And let me stop that one. And tweaking the C, as you can see, it's like, it's weird, huh? It's weird, and it's nice. Let me show you it. Tweaking the C, okay, the C is the amount of y-axis. As you can see, if I make it 4 exactly, you can see it's 4 here. If I make it like 2 exactly, it is 2 here. And if I make it minus, it will go to be minus 2, minus 4, minus 6. That how you get an intuition about how the support vector machine work. It works by tuning those parameters. I'm not going to go deeply in the math behind them and the Lagrangian and all this stuff. I'm just like I want you to have an intuition how we can control that line and how we draw that plane, that hyperplane, by tweaking those variables, especially those variables, the slope and the constant here. By tweaking them, we can achieve like we can choose the best line between our data. Let me show you another one. Like it's here. By the way, you can visit that website, demos.com. So you can visit them and see the support vector machine as a live. So you can tweak them and you can see how the support vector machine is working. Let me just zoom in. As you can see, the support vector machine, and we are tweaking the slope and so we can achieve the best one, which separates the data. I think that is not the one, that one, you can see. So tweaking these constants, okay, going to help you draw the best, not help you, it's like help the computer to draw the best decision boundary and then the best line which is separating the data, and which we can use it for classification or regression. Let's go back to our slides now. The last idea about support vector machine is using them in prediction. We are going to reverse our work. Instead of using them for classification, we have class 1 and class 2. No, we are going to use them for prediction. Any point inside the boundary, it's going to be predicted. We can predict the future data, like those points going to be inside the boundary. As you can see, we don't have classes here. We have a boundary, we have a line, and have a boundary, and that is much like if we compare support vector machine to something like linear regression. We are going to have it later. Support vector machine is perform further more well than linear regression. Why? Because if you have a data have like scattering, like have outliers, and like your data is not like a linear, you can't have a very sharp line for your data. You can use support vector machine, and you can increase the boundary to contain almost most of all your data, and that's going to give you much more and better performance than linear regression data. So a recap, we talked about support vector machine. It's an algorithm which you can use for classifying the data between like two different classes, male, female, cats and dogs, and other stuff. And the pretty thing about support vector machine that you can use it for predicting future data, and we have a comparison between linear logistic regression, and we have a comparison between a logistic classifier and support vector machine as a classifier, and we show that support vector machine is performing much better than normal logistic regression. And we have we show that we can use support vector machine for linear regression for predicting future data. So it's an algorithm which have a wide usage in our AI things. You can use it for even with the neural networks to as a classifier on the final layers. You can use it in speech recognition and text classification, and it's a fast algorithm. So as you can apply them easily with low competition, especially applying the kernel tricks and doing the competition in the lower dimension and mapping them into the higher dimensions. So like as a final, I invited you to totally encourage you to watch that kind of that linear algebra course from Gilbert. It's a wonderful course. It's like 36 lecture. It's long. Be patient. It's a wonderful course. It's going to give you a nice tool to use in your AI career. That's my recommendation for today for you, that kind of course. And thank you. Thanks everyone. Thanks for attending. Thank you.